Before we look at the first and second derivatives in detail, let's see if we can make some predictions. First of all, if our graph is correct so far, we expect to see that the function is increasing to a certain point and then decreasing, and then past the asymptote, decreasing and then increasing. So when we look at the sign of the first derivative, we expect it to go positive, negative, and then negative, positive. We also expect to find a relative maximum somewhere around here to the left of the vertical asymptote, and a relative minimum somewhere to the right of the vertical asymptote. Later on, when we take second derivatives, we expect to find that the graph is concave down first, and then on the other side of the vertical asymptote, concave up. So we expect to have the second derivative negative on the left of the asymptote and positive on the right side of the asymptote. Let's see if that's how it works out. To calculate the first derivative, we'll need to use the quotient rule. So it'll be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Let's simplify that numerator sum. Multiplying these two binomials, I have 2x squared minus 3x plus 1, and distributing this minus sign, minus x squared plus x minus 4, all over x minus 1 squared. Combining like terms, 2x squared minus x squared is x squared, minus 3x plus x is minus 2x, and 1 minus 4 is minus 3. That numerator actually factors as x minus 3 times x plus 1. So that's my first derivative. Now, the possible possible critical numbers are going to be the places where the first derivative is 0 or undefined. So notice that this is undefined when x is equal to negative 1. But that's not actually going to count as a critical number, because remember that is the location of our vertical asymptote. But it's still important. We'll put that on our number line. Notice that f prime is equal to 0 when the numerator is equal to 0. So that'll be when x equals 3, and also when x equals negative 1. These are our critical numbers. So let's draw a number line for the first derivative. I'm going to put the vertical asymptote on. The vertical asymptote happened at 1. And I'll write VA above it. We also have a critical number at x equals 3, which is over here, and a critical number at x equals negative 1. And at each of those, the first derivative is 0. So I'll write a 0 up there on the number line. And now I have 4 intervals to test. From negative infinity to negative 1, from negative 1 to 1, from 1 to 3, and from 3 to infinity. So we pick a representative from each interval, maybe negative 2 in the first interval, 0 in the second, 2 in the third, and 4 in the fourth. And we'll substitute each one of those into the first derivative. And I'm going to use the factored form. So for example, if I take f prime of negative 2, that's going to give me negative 5 times negative 1 over negative 3 squared, which is a positive number over a positive number. So I get the first derivative is positive on that interval. I encourage you to pause the video and substitute the numbers 0, 2, and 4 in, and see what the sign of the derivative is on each of those intervals. Assuming you've done that, you should find that the first derivative is negative on the second interval, negative on the third, and positive on the fourth. So when we talk about increasing and decreasing, the function f is going to be increasing on the intervals where the derivative is positive. So increasing from negative infinity to negative 1, and also from 3 to infinity, and decreasing from negative 1 to 1, and also from 1 to 3. Now when I go looking for relative maxima and minima, I'm going to be looking at the critical numbers, which are at negative 1 and 3. Remember, 1 is the location of a vertical asymptote, it's not a critical number. I'm going to look at what happens to the derivative nearby. Using the first derivative test, at negative 1, the derivative changes from positive to negative. So the function is increasing and then decreasing, which means that that's going to be the location of relative max. So there's a relative max at negative 1, comma, f of negative 1. Over here at 3, notice that the first derivative is negative, so decreasing, and then positive, increasing. So that's going to be the location of a relative min. So there's a relative min at 3, comma, f of 3. And we get the y coordinates by substituting back into the original function. So at negative 1, I'll have negative 1 squared minus negative 1 plus 4 over minus 1 minus 1. So that is, for 6 over negative 2 is negative 3. And if I substitute 3 into the original function, I should get, let's just check it. F of 3 is 9 minus 3 plus 4 over 3 minus 1, which is 10 over 2, or 5. So 3, 5. So let's use that to clean the graph up just a little bit more. We have a relative max at negative 1, negative 3. So let's maybe make this negative 1 on the x-axis. We can fine-tune this part of the graph a little bit. This point, remember, was at negative 4. A little above that at negative 3, negative 1, negative 3. It's going to be my relative max. So let's make the graph go through that point. And over here at 3, 5, fine-tuning a little bit more. Here's 2, here's 3. At 3, 5, there's going to be a relative minimum. And notice in terms of increasing and decreasing, the function is increasing to negative 1, decreasing from there to positive 1, decreasing from negative 1 to 3, increasing from 3 to infinity.